Hello my dear students, welcome to the next electronics and analog electronics. We have been discussing about power amplifiers in our previous lectures. Now let us see class A power amplifier and its conversion efficiency. So two types of class A amplifiers we are going to discuss. Before we move on, let us go through a quick review. Here the Q point and the input signal are so as to make output current flow for 360 degree. So there is no distortion. You are able to reproduce the signal completely over the entire 360 degree, or the full cycle can be reproduced in class A mode. So let us see the first type of class A amplifier, which is series fed directly coupled class A power amplifier. By direct coupling we mean that the load is collected here in the collector. That is RC is equal to RL now. The load is directly connected in the collector circuit. So this diagram is showing a class A amplifier. Here you can see we are not discussing about the details of biasing. This is a simple fixed bias circuit. We are concentrating on the series coupling or direct coupling here, and let us analyze this for its efficiency. Now the equation for the collector circuit is VCC equal to ICRL plus VCE, and you get IC equal to minus 1 by RL VCE plus VCC by RL. This is sufficient to plot the load line. So with that information, the graphical representation is like this. You can see this is VCC by RL when VCE equal to 0, when IC equal to 0 from the previous equation it is equal to VC is equal to VCC. Now VCEQ or the operating point you see is fixed at the middle of the active region. So this is the intersection of the base current corresponding to that, isn't it? IBQ is the base current corresponding to this point, this operating. So you fix the operating point for this particular base current IBQ. Now VCEQ is equal to VCC minus ICQ into RL. The DC under the DC conditions, you can see that when there is no AC signal, this VCEQ is operating point, VCEQ ICQ, and VCEQ equal to VCC minus ICQ into RL. And you can see the DC power input PDC equal to VCC into ICQ. This is the DC power input. Now let's see what is the AC power. So AC power, for that you have Vm is equal to Vpp by 2. From this previous figure you can see this is the peak to peak value from V minimum to V max is a peak to peak value. So the maximum value of VCE is Vm. Now Vm is Vpp by 2, or it is Vmax minus Vmin by 2. Similarly, Im is Ipp by 2, or Imax minus Imin by 2. Now using RMS values, if you compute the power, PAC is VRMS into IRMS. And if you substitute in terms of RL is the load resistance. So IRMS square into RL, or PAC is VRMS square by RL. If you compute using peak values, you can replace this VRMS IRMS with Vm by root 2. Or if you replace it like this, PAC will be Vm Im by 2. And in terms of RL, you will get Vm square by 2RL. Just you have replaced VRMS with Vm by root 2. That's all. Then in terms of peak value, if you compute, you will get PAC as Vm Im by 2. What is Vm in terms of peak value? It is V peak to peak by 2. And Im is I peak to peak by 2. Substitute, you will get an expression like this, Vpp square by 8RL or Vpp Ipp by 8. Like that you get 3 expressions in terms of RL, current and voltage. Okay, now Vpp is nothing but Vmax minus Vmin, and Ipp is Imax minus Imin. So the general expression for AC power is equal to Vmax minus Vmin into Imax minus Imin by 8. We are replacing this peak to peak and I peak to peak with a Vmax minus Vmin and Imax minus Imin. This is the expression for output AC power. Now, what is efficiency? Efficiency of an amplifier represents the amount of AC power delivered or transferred to the load from DC source, that is accepting the DC power input, and the generalized expression is PAC by PDC into 100. This we have already discussed, conversion efficiency. Now for this class A operation, what is the expression for efficiency? Vmax minus Vmin into Imax minus Imin by 8 VCC ICQ into 100. This is the conversion efficiency of a class A amplifier. Is it clear? Now, maximum efficiency. To find the maximum efficiency, we are assuming maximum swings for both output voltage and output current. That is, maximum swing in the sense this is the operating point Q. So this is ICQ and this is VCEQ. Okay. From this, it is going to, so this is fixed at the center of the active region, which means this will be half of the saturation current and this will be half of VCC. VCEQ will be half of VCC and this will be half of this saturation value VCC by RL. So Imax is 2 ICQ. This is not this. So this value from here to here it will be 2 ICQ and from here to here it will be VCC. Okay. Now we are assuming that current is swinging to its maximum and voltage is also swinging to its maximum. That is, the maximum power is taken as output. So which means under this condition you will get the maximum efficiency of this particular power amplifier. So to find the maximum efficiency, if we assume full swing, Vmax will be VCC I have just mentioned and V minimum will be 0. Imax will be 2 ICQ and I minimum will be 0. So if you substitute these values for Vmax, Imax, V minimum and I minimum, VCC minus 0 into 2 ICQ minus 0 divided by 8 VCC ICQ is the efficiency. Now when you simplify, what do you get? This you can cancel this VCC, ICQ and 2 by 8 you get the factor. What is that? 25%. So which means if you assume full swing for voltage and current, this class A series fed or directly coupled class A amplifier will have a maximum efficiency of 25% only. We have discussed why we need transformer coupling. This is the reason. The efficiency is very small for direct coupling. It is below 25%. This is the maximum possible efficiency. In actual, for a practical circuit, it will be much less than 25%. Because again, if we consider the drop in the transistor, the power dissipation in the transistor, or the power dissipation in the RE resistance, if emitter biasing is there, RE resistance, all these will contribute to an efficiency which is less than 25%. So very low efficiency is the biggest disadvantage of class A amplifier. Excuse me. Now the power flow diagram is simply showing you what is happening to the power that is drawn by the amplifier. So the power drawn is the input power, DC input power. So from that power is lost in the RL, and that is the DC power which is lost in RL. Now power is delivered to the transistor. What is happening to the power delivered to the transistor? AC power is developed across RL, which is PAC, and power is lost in the collector in the form of heat. That is the DC power which is lost in the transistor. So in this case, there is the additional power which is lost in RL as far as direct coupling is concerned. This term won't be there in transformer coupling, but these two losses will be there. The AC power will be developed across the load, and the power will be lost in the transistor, but this power loss, DC power loss in RL, is avoided when you go for transformer coupling. Next we'll see the advantages and disadvantages. What are the advantages of directly coupled Class A amplifier? The circuit is simple to design and implement. Load is connected directly in the collector circuit, hence output transformer is not necessary. This makes the circuit cheaper and less number of components required as load is directly coupled. But the disadvantages are, as we mentioned, the load resistance is directly connected in the collector and it carries the quiescent current, collector current, that is ICQ drop will be there across RL. DC drop will be there. This causes considerable wastage of power. Power dissipation is more, so heat sink will be necessary to dissipate the power. Then output impedance is high, hence circuit cannot be used for low impedance loads such as loudspeakers, and the efficiency is very poor due to large power dissipation. So what is the difference between a voltage amplifier and this amplifier? The only difference is that since it is a power amplifier, it has to handle large voltage and current, and power transistor has to be used. But because of RL, there will be huge losses occurring here, and efficiency is maximum 25% only. Next, we will discuss transformer coupled class A power amplifier. The difference is you are replacing RL with a transformer. Here, turns ratio is marked as N is to 1. You are familiar with N1 is to N2. That's all. That's only difference. And the load can be a loudspeaker. Okay, you know this impedance matching concept. So RL will be reflected as RL dash is equal to N1 by N2 the whole square into RL. This you are already familiar with, the impedance matching using the transformer, and we can start our discussion. Here also the DC power input PDC will be equal to VCC into ICQ. You are fixing the operating point in the middle of the active region since it is class A power amplifier and you want to get the whole signal at its output. Okay. Now, let us see the load line for transformer coupled class A amplifier. You observe one thing here, we need both DC load line and AC load line. Why? Because as far as this circuit is concerned, under DC conditions, when there is no signal supplied, when this signal is not applied to this base of this transistor in the DC condition, we are assuming the DC resistance to be 0. Actually, the DC resistance of this transformer is very small, so we are assuming it to be 0, and we are neglecting this RE drop as well. If under such condition, you can say that the DC load line will have an infinite resistance, or it will be a line which is parallel to this collector current. So DC load line will be passing through VCC, and you are fixing the base current at a particular value IBQ, which is fixing this operating point at the middle of the active region. So this is the DC load line. So under DC conditions, VCEQ equal to VCC. We are neglecting all the drops because this is negligible. This RDC drop and RE drop are negligible. So we say that this collector to emitter voltage VCE is equal to VCC under quiescent condition. So in the if we assume like that, VCEQ equal to VCC. That is what is shown here. This is the VCEQ value which is equal to VCC, and DC load line is passing through that. What about the AC load line? So this AC load line, what is coming as AC load? AC load, as I mentioned, this RL is reflected as RL dash to this collector circuit. So RL dash is the resistance. This is RL dash. RL dash is the resistance which is coming into picture when you connect the transformer at the output. So minus 1 by RL dash will be the slope of the AC load line. Okay, AC load will be RL dash. So minus 1 by RL dash. Such an AC load line, if you draw passing through this Q point, you get the limiting values of this particular condition. So VCC will be here. So the VCE maximum value will be somewhere here, and IC maximum saturation value will be here, such that its slope is minus 1 by RL and it is passing through this Q point. Okay. Now we'll see what is PAC. Similar to the previous analysis, PAC will be Vmax. Here you see Vmax minus Vmin into Imax minus Iminimum divided by 8. Now again, percentage efficiency will be Vmax minus Vmin into Imax minus Imin by 8 VCC. ICQ, the expression is the same, but when you go for the maximum efficiency, when you try to see what is the maximum efficiency, you will see that you have to assume full swing. When you assume full swing, the difference here is this ICQ is the operating current, IC quiescent condition collector current, and VCEQ is equal to, it is marked as VCEC because VCEQ equal to VCC here for this transformer coupling. So this is equal to VCC. So if you assume a sinusoid which is going to full swing, if this is VCC, this will be 2 VCC and this will be 0. Similarly, if this is ICQ, this will be 2 ICQ if you assume full swing of current, and this minimum value will be 0. So Vmin is 0, Vmax is 2 VCC, Imin is 0 and Imax is 2 ICQ for maximum swing. Substitute these values in our expression for efficiency. In that case, what will you get? 2 VCC minus 0 into 2 ICQ minus 0 divided by 8 times VCC ICQ. And on simplification, you will see that the maximum efficiency of a class A transformer coupled amplifier is 50%. Whereas for series or for direct coupling, it is 25% only. Now, if you want to find the AC power developed in primary, these are the expressions you need to be familiarized with. PAC is equal to V1 RMS into I1 RMS. And PAC is equal to I1 RMS square into RL dash. Now this PAC, if you express in terms of the peak value, it is V1M I1M by root 2 into by root 2. And similarly, if you substitute here for maximum value, then again this I1 RMS square RL dash will change to I1 maximum square RL dash by 2. That root 2 will become 2. Like that you get these many expressions for AC power which is developed in primary. These will be required when you do the problems. Okay, you should have this understanding of this RL dash. This RL dash is there. AC power can be expressed as VRMS into IRMS or VRMS square by RL dash, because RL dash is the resistance of the load reflected to the primary. So these expressions can be substituted in this efficiency expressions also. That is you may need these expressions when you do the problems. So this slide is explaining why the DC load line is a vertical line and all. You can go through these. Now, what are the advantages? The advantages of transformer coupled efficiency is higher than direct coupled. Then a DC bias current that flows through the load in case of direct coupled is stopped in case of transformer coupled. That is, in the case of transformer coupled, the DC resistance of the load side is 0. The impedance matching required for maximum power transfer is possible. Impedance matching is possible because of transformer coupling. Now, what are the disadvantages? This transformer makes the circuit bulkier, heavier and costlier compared to directly coupled. The circuit is complicated to design and implement compared to the direct coupled. The frequency response will also be poor. So, that is the only thing you have to consider when you have to compare the direct coupling and transformer coupling. So, we can do some problems based on this. We'll discuss in the class. Thank you.